We now discuss the classical limit of wave mechanics. In the last class, we have defined the general form of wave function psi of xt as that is equal to under root rho e raised to is over h cross. Okay, let me put it as equation 1. And we know the time dependent wave equation is minus h bar square over 2m del square psi plus b psi equal to h cross dou psi by dou t. Okay, let me substitute this value of psi of x into the time dependent wave equation. We will get the equation 3. Okay, I just jumped into equation 3. I'll provide the derivation through which we have arrived this equation either at the end of this video or in another video under the title the classical limit miscellaneous. Okay, so when we substitute this one, we got the equation 3 as minus h bar square over 2m del square under root rho plus 2a over h cross del under root rho dot del s. This both are vectors del under root rho del s minus 1 over h bar square under root rho mod square of the mod del s plus I over h cross under root rho del square s plus under root rho v equal to I h cross in the bracket dou under root dou by dou t of under root rho plus I over h cross under root rho dou s by dou t. Okay, that is equation 3. When we multiply the term outside the bracket minus h bar square over 2m into the terms inside this bracket, we will get the step or equation 4. Okay, and now if the value of h cross is so small, let us assume h cross del square s, h cross mod del square s is less than of mod del s, square of the mod del s. And let me put it as equation x. Let it be there. We'll discuss the physical significance of this condition later. Okay, now we go to when h tends to 0. Okay, if h tends to 0, then we can ignore the terms in the equation 4 having h cross. Okay, here we are taking the condition that h cross tends to 0. So we can ignore the terms with h cross in the equation 4. So we will get the equation, we can manipulate the equation as, we can take the terms, the remaining terms which don't have h cross as 1 over 2m under root rho mod del s whole square plus under root rho b equal to minus this having h cross, so minus under root rho dou s by dou t. Okay, the terms having h cross are this having h cross and this contain h cross, this contain h cross and this contain h cross. So the remaining terms I have chosen here. So 1 over 2m under root rho mod del s square plus under root rho b equal to minus under root rho dou s by dou t. So this get cancelled, this under root rho terms get cancelled, and the remaining terms are mod del s square, square of the mod del s plus square of the mod del s plus b plus dou by dou t of, this is minus dou s by dou t. So when we are taking the left side, we will get plus dou s by dou t equal to 0. Okay, this is equation 5. Okay, for a while, let us go to classical mechanics. Okay, the Hamiltonian h plus dou s by dou t equal to 0 is the Hamilton-Jacobi equation in classical mechanics, where s is the Hamilton's principal's function. Okay, s is a function of x and t, and we can be written this as w of x minus at. Okay, this function is separable, so we can be written as function of x minus function of t. Okay, where w of x is known as Hamilton's characteristic function. Okay, so in the last class, when we compare with the general form of the wave function as well as the equation of the plane wave, we got what is s, and we got delta s equal to momentum p. Okay, so look at this equation 5. Here mod delta s square is in the dimension of p square over 2m plus this is potential term v of x. So the kinetic energy term plus potential energy term is the total energy term plus dou s by dou t equal to 0. That is, here in classical mechanics, we can compare, when we compare with this is a Hamiltonian. So this is Hamiltonian plus dou s by dou t equal to 0. When we compare with the Hamilton-Jacobi equation in classical mechanics, this is similar to Hamilton-Jacobi equation. Okay, so that means when the h cross tends to 0, the wave mechanics contain the classical mechanics. Okay, when h cross tends to 0, our equation become Hamilton-Jacobi equation. Our equation is similar to Hamilton-Jacobi equation. That means when h cross becomes 0, the wave mechanics contain classical mechanics. Okay. This is the Hamilton's principal function s of xt and is separable as a function of position, some function of x and function of time. Okay, so it can be written as w of x minus at, and that is equation 7. The general form of wave function is psi of xt is proportional to e raised to is over h cross, and the equation of a plane wave is psi of xt is proportional to e raised to ip dot x minus et over h cross. Okay, if I compare both of these equations, I can write s of xt equal to p dot x minus et. Okay, and that, if that I compare with the Hamilton's principal function, can be written as s of xt equal to function of position w of x minus this constant is the energy. Okay, this constant is the energy in wave mechanics. To explain something important, I'll write this equation as e raised to I kx minus omega t. Equation of a wave e raised to I kx minus omega t. And if I compare this with this one, I can write s over h cross equal to kx minus omega t. Okay, this k we know, this is the wave vector, k equal to 2 pi over lambda, and this is the velocity. Okay, that means this portion will give you the spatial information and this portion will give you the velocity of the wave. Okay, this h cross is a constant. Compare with this portion will give you the spatial information about a wave, and this one will give the velocity of the wave. So I can draw a wave, sinusoidal wave. At a particular time, this wave will look like this. Okay, after a time t, this is a traveling wave. After a time t, this wave will move like this. That means this wave is traveling in this direction. That means we can find out how much distance it traveled within that time. Okay, that means this portion, this is the phase, this portion will give the information, all information about the wave. This portion will give the spatial information, this portion will give the velocity. So we can find out how the wave advances with respect to time. Okay, next, when we consider this figure, this is the central portion of this figure. I am defining, here is the maximum probability of finding the particle. Okay, so I can draw the wave function. That means the wave function is spreading all over the space. Okay, in 3 dimensions, all over the space, the wave function is spreading. If I joined the points having same phase, the points having the same phase at a particular time t, I'll get many concentric circles. Okay, and by the time being, this concentric circles is advances. This concentric circles are advancing with respect to time, and we can compare that with the wavefronts in geometrical optics explained by Christian Huygens. Okay, so this concentric circles advances like if I drop a stone in calm pool of water, the circular ripples will spread out. From the point of impact. Okay, I can compare this with this one. Here this is probability of finding the particle. Here this is the wave function. I am representing the probability of finding the particle with a wave function, or the presence of a particle. I am representing the presence of a particle with a wave function, and the wave function advances like this, as if the same phase, the points of same phase advances as if the concentric circles or the ripples advances in a calm pool of water when I drop a stone. Okay, that means I can compare the wave mechanics. with the geometrical optics. Okay, so if suddenly the phase change happens in some particular direction, and this concentric circles become like this. Okay, that means the maximum phase change happens at this portion. That means the direction of del S is in this portion. So we can sense the particle starts to move in this direction. Okay, this is the direction of probability flux. So if the phase change happens in this direction, perpendicular to this wavefront, that means we can sense the particle starts to move in that direction. Okay, so in many